In this section, we're going to talk about the fundamental theorem of calculus, in which there are two parts. This is usually a large punchline at the end of a Calculus 1 semester. Let's first start by explaining what this theorem says. We're going to do a quick example to see how it works, and then we're going to prove this theorem as well. So the first part of the fundamental theorem of calculus is given by if a function is a continuous function on a to b, it must be continuous, and capital F is some antiderivative of lowercase f on the interval a to b, which must be a closed interval as shown. Then the integral from a to b of f of x dx is equal to capital F of b minus capital F of a. One way to kind of understand what's going on with this fundamental theorem is that this gives us a way to evaluate definite integrals using just an antiderivative. In section 4.1, we talked about how to find indefinite integrals, and we saw that we can just find all antiderivatives of that function. And this is going to be the tie-in to definite integrals as well. We can use an antiderivative to find the area under the curve, which is what a definite integral is defined to be. So let's go over an example, and then we'll go ahead and prove this statement as well. Here we have the integral from 1 to 3 of the function 3x squared. Remember, the dx is telling us with respect to x. This is a mathematical sentence. Each part of it is important. This says to find the area under the function 3x squared from 1 to 3. But we're not going to think about area. We're just going to think about antiderivatives. And we can note that, first of all, that x cubed is an antiderivative of 3x squared. And again, that's because the derivative of x cubed is 3x squared. So what we're going to do is some notation to deal with this integral. We are going to write the antiderivative, an antiderivative, x cubed, and we're going to write this with a little vertical bar with a 1 on the bottom and a 3 on the top, corresponding to the bounds at the beginning. This bar means to evaluate from x equals 1 to x equals 3. And what that's going to mean is we are going to plug in 3, and we're going to subtract plugging in 1. This is exactly this f of b minus f of a in the statement of the theorem. So this again is shorthand for some long English sentence that we don't have to write out each time. And it's important to have that there, and it's important to know when it's going to be there and when it's going to go away. So this says x cubed evaluated from 1 to 3. We're going to plug in the 3 and then subtract off plugging in the 1. This is going to give us 3 cubed minus 1 cubed. That is the antiderivative where I plug in the top bound minus the antiderivative where I plug in the lower bound. And this will give us 27 minus 1, or 26, which is the area under the curve, and we didn't have to think about area to deal with it. That is the nice part of the fundamental theorem of calculus. So we're going to go ahead and prove this theorem now. To start, let's restate the theorem. We have that the integral from a to b of f of x dx is going to be equal to capital F of b minus capital F of a. What we're going to do is we are going to start with a partition of the interval a, b into n subintervals, which is a fancy way of saying we're going to take this interval a to b And we're just going to chop this up into n equal parts. So we're going to give a label to A. We're going to call that x0. B we're going to call xn. And we're going to have a bunch of equal parts in the middle. And we're going to give names to all these x values, x1, x2, x3, so on. Here's x sub n minus 1, and everything in between for any value of n. Note that in this case, delta x is going to be x sub 1 minus x sub 0. That's actually going to be equal to x sub 2 minus x sub 1. It's going to be equal to all those differences. X sub n minus x sub n minus 1, everything in between. And we can just say that's going to be equal to x sub I minus x sub I minus 1. All of those are the same. That's our value of delta x. That's going to be important in this proof. What we're doing is we are chopping up this interval as we would for a Riemann sum. The left-right rule, the midpoint rule, the upper-lower sum idea. Except we're not going to build rectangles out of this at this moment. We're just going to think about these values. So to start with this proof, we are going to show that the right-hand side is equal to the left-hand side. And I should state that this proof is good to understand what's going on. It uses a lot of what we learned in calculus from the first day, but you are not expected to know this proof. It's a difficult proof. It's going to take us 2 pages to go through. There's a lot of difficult steps. So don't worry about memorizing this proof. Just try to understand what is going on. So here we're going to start with f of b minus f of a, but we're going to think about it instead as f of x sub n minus f of x sub 0. The reason we're doing that is just because we're going to use all these x values instead. So then, from there, we are going to write this as f of x sub n, and we're going to have a minus f of x sub 0 at the end, but in between, I'm going to add and subtract the same value a number of times. So I'm going to subtract an f of x sub n minus 1, and I'm also going to add that value right back. This is maybe an odd step to do, but as long as I add and subtract the same value, I am not changing the value of the expression. I'm going to do that a few more times. In fact, n more times. I'm going to subtract off an f of x sub n minus 2, and I'm going to add it right back. And I'm going to continue doing that until I get down to subtracting off an f of x sub 1, where I'm going to add an f of x sub 1 right back. And then finally, from the very beginning, I have an f of x naught. So although it looks kind of nuts, I have that this is all equal to f of b minus f of a, and I'm going to continue to mess with this expression till I get a Riemann sum kind of like thing that I'm going to relate to the integral. So next step here is I'm going to group some of these terms together. I'm going to group the f of x sub n and f of x sub n minus 1, and in fact, every consecutive terms I'm going to group together. Note that this dot 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 kind of makes it crazy. This f of x sub n minus 2 is actually going to be combined with a minus f of x sub n minus 3. I just need to stop writing these at some point and write dot dot dot. So although this looks like maybe one big grouping, this is a lot of groupings. I'm just not going to write every one. Then finally, f of x sub 1 minus f of x naught. Then what I'm going to do is I'm going to multiply and divide by the same value, and that value is going to be delta x. So I'm going to multiply this first thing by delta x and divide by delta x. I can do that because as long as I multiply and divide by the same number, it's like multiplying by 1. And I'm going to do that for all of these groupings. I'm taking this f of b minus f of a thing, and I'm going to try to rewrite it like some Riemann sum, and we're going to show how it's going to look like that. So again, I need to do some rewriting here. One thing I'm going to do is I'm going to factor out a delta x out of every single term in this sum. Okay, I don't need to write delta x each time multiplied by, but I'm just going to factor that out. I'm going to keep the delta x's on the bottom because that's going to be important. And here I'm going to have, let's look at the first term, f of x sub n minus f of x sub n minus 1. Instead of writing just delta x, I'm going to rewrite it as x sub n minus x sub n minus 1, which is one of the ways that I could have written delta x at the beginning. It's the length of every subinterval because they're all equal. So I'm going to write this as x sub n minus x sub n minus 1. For the next guy, I have f of x sub n minus 1 plus f of x, minus f of x sub n minus 2. And I'm going to divide that by not delta x, but x sub n minus 1 minus x sub n minus 2. And I'm going to continue doing that for all these terms until I get to the last one, which is going to be f of x sub 1 minus f of x naught divided by, this time, x1 minus x naught. Now I have this expression, and now is the time that I'm going to try to relate this capital F of f, or capital F, to lowercase f. That's the really big step here. And I'm going to use the mean value theorem. I'm going to write it down very quickly, but it might be worth to go back and check what that theorem says. We have not used it very often, but it's very, very important. It's going to be very crucial in this step right here. So the mean value theorem says that if f is continuous and differentiable, as we need those, then there exists a c in the interval a to b such that the derivative of c is equal to, or so the derivative at c is going to be equal to f of b minus f of a over b minus a. And let's just take a look at that statement of that theorem. Let's just try to relate it back to what I have written down right now. I'm not going to think about the delta x out in front. That's going to come in later. But in all of these terms, I have a bunch of things added together, and each of those things look kind of like that f of b minus f of a over b minus a, except instead of writing a and b, I have other values written. I am going to rework the mean value theorem just so it works for those values instead. So let's go ahead and do that now. So here's the mean value theorem, but kind of reworked here. This says that there is not just a c, we're going to call it a c sub I in the interval x sub I minus 1 to x sub I, such that the derivative of capital F at c sub I is going to be equal to f of x sub I minus f of x sub I minus 1 divided by x sub I minus x sub I minus 1. And big note here is that the derivative of capital F of x is equal to lowercase f of x because capital F is an antiderivative of lowercase f. Here's our relationship that we have, and it's the mean value theorem that allows us to transfer in between the function and its derivative, or the antiderivative and the original function. So now let's rewrite our big equal sign here. What we're having is this is going to be equal to, we had our delta x out front, but this time I'm not going to write this capital F minus capital F kind of thing. I'm going to write that as f of C1 plus, sorry, this should be C sub n, the way we wrote it before. F of Cn plus f of C sub n minus 1 plus all the way down to f of C1. All of those values come from, again, the mean value theorem says this is going to be equal to f of C sub I. That's what we said in the green writing right there. All of those difference quotients are going to be equal to the function values. And we're going to rewrite this as a sum using sigma notation. This is going to be the sum from I equals 1 to n of f of C sub I times delta x. I'm going to bring delta x inside the sum so that we can see that this is exactly a Riemann sum. We're almost done now. Now we are going to take the limit as n goes to infinity on both sides of our equal sign. So I have that this sum is equal to f of b, capital F of b, minus capital F of a. And I'm going to take the limit as n goes to infinity on both sides. In the last two sections, we talked about what this limit of this sum is going to be. This is exactly the definition of the definite integral from a to b of f of x dx. And when I'm taking the limit of these values, f of b minus f of a is a constant. So when I take the limit of a constant, I am left with just the constant itself. It has no n in there, so nothing really happens with the limit. And that is our result of the proof. Once again, you are not going to be expected to replicate this proof, but it has very important ideas. It talks about Riemann sums. It talks about the definition of the definite integral, which is a very important topic from the last two sections. It talks about the mean value theorem and the relationship between a function and its derivative. And there's a bunch of nice algebraic steps that continue to show up throughout your mathematical careers. So now that we have this fundamental theorem of calculus, we are able to calculate definite integrals much quicker using just an antiderivative. In fact, if we can find the antiderivative, this is a pretty quick process. So, first example here, we have the integral from negative pi over 4 to pi over 4 of 3 secant squared dx. First thing we're going to do, we should always get into the habit of, is maybe writing this as 3 times this integral. I can take out constants out in front of the integral, and that makes finding antiderivatives that much easier. So now that I have that 3 out in front, I need to find some antiderivative of secant squared. I need to think about what function has a derivative that is equal to secant squared, and the function that works there is tangent of x. And I'm going to evaluate from negative pi over 4 bar has a meaning. It means to plug in the top bound minus plugging in the bottom bound. This will give us 3 times tangent of pi over 4 minus tangent of negative pi over 4. Tangent of pi over 4 is 1. Tangent of negative pi over 4 is negative 1. This is going to be 3 times 2, 4, 6. Now, one note I wanted to make about this example before we go any further is we need to find just one antiderivative of secant squared. In section 4.1, we learned that there's not just one antiderivative, there are infinitely many antiderivatives, and we can write those using a plus c. So let's just alter this example real quick, thinking about the plus c inside of there. Maybe you wanted to think about an antiderivative of secant squared as tangent of x plus c. Well, I could work that in. I could say plug in pi over 4 to that function. You have the plus c there. Plug in the negative pi over 4 and have the plus c there. But you'll note that the plus c's are going to cancel out, and we're left with just what we had before. And this is why we don't need to write plus c when doing definite integrals. And there's actually two meanings behind that. We don't need to write plus c when we find an antiderivative, and we definitely don't want to write plus c at the end of this because that's not what the plus c represents. This is an area, and if we add a constant to that area, we're not actually finding an area. We're saying that could be any value. So we're definitely not going to write plus c at the end, and we don't have to write plus c using the antiderivative. So, going on, let's look at another example. We have the integral from 0 to 1 of x minus square root of x over 3. This, at first glance, maybe looks like a pretty tough integral, but if we get into this habit of pulling constants out in front, this becomes much easier once we pull the constant out in front. And we can note that the constant here is 1/3. It's kind of hidden because it's written as a fraction. There's a 1/3 constant, and if we take that out, we are left with x minus square root of x. And although I'm not going to maybe write it like this, we could think about this as two separate antiderivatives. The integral of x minus the integral of square root of x. We can always just anti-differentiate over addition and subtraction very easily. So here we go. We have this 1/3 out in front, and we're trying to find an antiderivative of x minus square root of x. We're going to use the reverse power rule. Note that square root of x we can rewrite as x to the 1/2 power. And in both these cases, we're going to add 1 to the exponent, and we're going to divide by that new exponent. So for the first one, I'm going to add 1 to the exponent. That gives me a x squared, and I'm going to divide by that new exponent 2. And for the second one, I'm going to add 1 to 1/2. That'll give me 3/2, and I'm going to divide by that new exponent 3/2. That's my antiderivative, and I'm going to evaluate that from 0 to 1. Maybe it's useful to simplify this a little bit. So we'll write this as, maybe we'll bring in the 1/3 inside. This will be a 1/6 x squared minus 2/9 x to the 3/2 evaluated from 0 to 1. That simplification is not necessary, but it's something that we could do, so I wanted to show that. And here we could plug in 1. This will give us a 1/6 1 squared minus a 2/9 1 to the 3/2 minus plugging in 0, 1/6 0 squared minus 2/9 0 to the 3/2. 1/6 times 1 squared is 1/6. 2/9 times 1 to the 3/2 is 2/9. 1/6 times 0 squared is 0. 2/9 times 0 to the 3/2 is 0. And this is going to be equal to 1/6 minus 2/9. We need to find a common denominator. That's going to be 18 that we can combine these. 3/18 minus 4/18. This will give us a negative 1/18. The answer is negative, which would mean that if I could graph this function and look at the area under the curve, the area would be mostly below the x-axis and have a negative total area. Here's one thing I want you to look out for when you're doing integrals. It is a very common thing to do for Calc 1 students and Calc 2 students, is when you see a 0 in the bottom bound, that when you plug that into a lot of functions, it's just going to be 0 at the end. So students start to ignore the bottom bound of 0. That is a very dangerous thing to do, and there are plenty of examples where you plug in 0 and you will not get 0 out. It is a lazy thing to do, and you should try to ignore that shortcut as much as possible. Here's another example. We have the integral from 1 to 4 of 3 minus absolute value of x minus 3. And the reason we're doing this example is, how do we deal with the absolute value of something? Well, it's important to know, what does this absolute value actually represent? The absolute value of x minus 3 is going to be equal to negative x minus 3 on some interval, and it's going to be equal to positive x minus 3 on some interval. When the value x minus 3 is negative, it's going to be equal to negative that value. So this is going to be if x is less than 3. That's from this x minus 3 being less than 0. We get our x less than 3. And this is going to be equal to positive x minus 3 if x is greater than 3 or greater than or equal to 3. The difficulty of the absolute value function is the only way that we can really deal with it is as two separate functions that we can combine together as a piecewise function. So what we're going to do is, this big integral we're going to rewrite as the integral from 1 to 3 of a function dx plus the integral from 3 to 4 of some function dx. We need to break it up into these two different intervals, because when x is less than 3, I have one function that I'm going to deal with, and when x is greater than or equal to 3, I have another function that I'm going to deal with. So, when x is less than 3, so I'm on the interval 1 to 3 here, I can rewrite this as 3 minus negative x minus 3. And when I'm on the interval 3 to 4, I can write this as 3 minus x minus 3. Rewriting this, I have the integral 1 to 3. Let's simplify that. That's going to be 3 plus x minus 3, which is going to give us just x. And the interval from 3 to 4, will be a 3 minus x plus 3 will give us a 6 minus x. Now I have to take the antiderivative. In the first one, we have the reverse power rule. This is going to be equal to 1/2 x squared evaluated from 1 to 3. And for 6 minus x, I'm going to have 6x as the antiderivative of 6, and then minus 1/2 x squared, the antiderivative of negative x, this time evaluated from 3 to 4. Two different things to evaluate. So here we're going to have 1/2 3 squared, plugging in the top bound, minus 1/2 1 squared, plugging in the bottom bound. And over here, a 6 times 4 minus 1/2 4 squared, plugging in the top bound, minus 6 times 3 minus 1/2 3 squared, plugging in the bottom bound. Simplifying, this will give us a 9/2 minus 1/2 plus 24 minus 8 minus 18, and make sure that you are distributing this negative to both terms. That's going to be a minus 9/2, a negative minus 9/2, which is going to be a positive 9/2. This is all going to simplify to 7 minus 1/2, or 13/2, which again represents the area under the curve of that function, but we can deal with that not thinking about area, just thinking about antiderivatives. There are a lot of other examples that we could look at. What's really the big key in understanding this is how do you find antiderivatives? That's section 4.1. There's some difficulty in that, getting used to. We're going to talk about in the next section some more techniques to find antiderivatives. And in Calc 2, you're going to spend a lot of time trying to find antiderivatives. It's a much harder task than finding derivatives. There's a lot of work that goes into that. If you know how to find it, then this process becomes pretty systematic as you go through it a few times. All right, this time we have an area problem, and we are going to rewrite it as an integral problem. So we're going to find the area of the region bounded by 4 things. The function 1 plus cubed root of x equals 0, x equals 8, and y equals 0. So let's start by graphing this function, or these functions. And we're going to start with the easier ones. So first of all, let's graph the function x equals 0. That is another name for the y-axis. Let's also graph the function x equals 8. That's a vertical line through the x value 8. Let's graph the function y equals 0, which is another name for the x-axis. And then the interesting one is 1 plus cubed root of x. To think about that function, cubed root of x looks like square root of x. And then 1 plus cubed root of x means we're going to move the cubed root of x up 1 unit. So cubed root of x looks like this. Cubed root of x plus 1, it's going to be moved up 1 unit. Maybe it's helpful to find exactly what this point is right here. When I plug 8 into 1 plus cubed root of x, that's going to give me a value of 3. That's not totally necessary in this problem, but it's good to maybe know what that value is. So what we're trying to find is the area that is trapped by all four of those functions, and that is going to be this area right here. And to find this area, we can note that this is just the area under the curve f of x from 0 to 8. I can think about area as a definite integral, and this is just relating the two. Maybe for this integral it is helpful to realize that cube root of x is x to the 1/3. And we can find an antiderivative. Here an antiderivative of 1 is x. And we're going to use the power rule on x to the 1/3. That's going to give us add 1 4/3, and we're going to divide by that new power. And we're going to evaluate this antiderivative from 0 to 8. So let's do that. That's going to give us an 8 plus 1 over 4/3 is the same as 3/4. 8 to the 4/3 minus 0 plus 3/4, 0 to the 4/3. And again, here the 0 is just going to go away. When you plug in 0, nothing's going to happen. But it's important to write that step down for the functions that's not going to be the case. Here we're going to have 8 plus 3/4, and we can actually deal with this 8 to the 4/3. This is the same as saying the cubed root of 8 to the 4th power, which is the same as 8 plus 3/4. Cubed root of 8 is 2. To the 4th power is going to be 16. It's going to be 3 times 16 divided by 4, which is the same as 3 times 4 is 12. This is going to give us a value of 20. Or since we're talking about area, we should put in a units squared. Again, there is a relationship between the definite integral and the area under the curve. Then we have some application of the definite integral. And it's going to be our first kind of application. There's going to be a lot more we're going to see in Chapter 7. This is going to be the average value of a function. Doing these problems itself is really not that bad, but kind of understanding why this formula works is interesting, and we're going to take a second to look at that. For this problem, I'm going to start kind of the same way I did the proof for the fundamental theorem of calculus. I'm going to break up the interval a to b into different subintervals. X sub 1, x sub 2, x sub 3, all the way to x sub n minus 1 and x sub n. And I am going to pick some c values in there. So here's c sub 1, c sub 2, c sub 3, c sub 4, c sub 5, all the way, and here's c sub n minus 1. It doesn't have to be the middle value, could be the left endpoint, could be the right endpoint, could be anything in between. So if I wanted to find the mean or average value of the f of c sub i's, there are n of those values. I should note real quick that that's not c sub n minus 1, that's c sub n, sorry. But if I want to find that, what I'm going to do is I'm going to add all of those values together. And I'm going to divide or multiply by 1 over n. That's how you find the average of a bunch of numbers. You add them all up and you divide by how many numbers there are. Then we're going to note that delta x, we have a formula for that. That's going to be b minus a over n, which means that 1 over n is going to be equal to delta x over b minus a, dividing by b minus a on both sides. Writing it like that, I now have delta x over b minus a, and then I'm going to rewrite this as a sum, I equals 1 to n of f of c sub I, and I'm going to write that as 1 over b minus a times the sum f of c sub I delta x, bringing the delta x into the sum. Then I'm going to take the limit as n goes to infinity. And we have our same sort of result that we had in the fundamental theorem. The limit of that sum is exactly the definite integral, but this time I have a 1 minus b minus a on the outside of it. And what this limit as n goes to infinity is giving us, this is now going to be the average value of the function. The idea here is that if you wanted to find the average value of the function, you could add up every single function value, divide by how many function values there are. Now, that doesn't make a lot of sense to do in reality because there are an infinite amount of function values, but we could think about a finite number of function values, n, do that process, and then let the limit as n goes to infinity. That's how we've been dealing with a lot of things in this calculus course. It's good to understand where that comes from. Again, you're not going to be responsible for this kind of argument, but it's good to see where it comes from. So now let's see an example of this, and we'll see that it's really not that bad. Find the average value of this function, t, 1 minus t squared, on the intervals 0 to 2. So in this case, a is 0, b is 2. So the average value is going to be equal to 1 over b minus a times the integral from 0 to 2 of t 1 minus t squared dt, as that's the variable that we're dealing with. This will be a 1/2 integral of 0 to 2. To deal with that t 1 minus t squared, we can distribute the t, give us a t minus t cubed. And the 1/2 out in front, find an antiderivative of t, that'll be 1/2 t squared. Find an antiderivative of t to the cube, that's going to be a 1/4 t to the 4th, reverse power rule on both of those. We're going to evaluate from 0 to 2. This will give us a 1/2 times 1/2 2 squared minus 1/2 2 to the 4th minus 1/2 0 squared minus 1/4 0 to the 4th. Again, plugging in 0 is not going to give us anything, but please write that every single time. And this will give us a 1/2 times 1/2 times 4 is going to be 2. 2 to the 4th is 16. Divided by 4 is 4. 1/2 times -2, or a -1, is the average value of the function. And now we're going to talk about the second part of the fundamental theorem of calculus. In this case, we're going to have that f is continuous on some open interval containing some value a. And for every x in the interval, we have this nasty looking statement. the derivative with respect to x of the integral a to x f of t dt is equal to the function value at x. This is a weird sort of theorem, but it's important to understand why we're talking about it. One is that this shows an inverse-like relationship between derivatives and integrals. We can kind of think about this as saying the derivative of the integral of a function is equal to the function itself. The derivative and the integral kind of cancel each other out. It's not exactly inverse, but it's inverse-like. Another thing that this theorem does is that it shows the existence of an antiderivative. In this case, the function a to x, the integral f of t dt, is an antiderivative of the function f of x. The existence of things is important. We need to find an antiderivative to evaluate definite integrals, but we don't even know if an antiderivative exists. This says that if f is continuous, then there does exist some antiderivative. It may not be easy to find, it may be hard to write down, but it does exist. So another thing we're thinking about this theorem is to understand the difference between the function and the number. So in the past few slides, we've been dealing with the integral from a to b. This integral is the area under the curve of f of x, and that is a value, that is a number. This integral, a to x f of t dt, is a function of x. I could plug in different values of x, and I will get different definite integrals out. To think about this graphically, it's like I have some function here, and I have some starting value a, and it's like I'm plugging in different x values. Maybe this is x equals 2, maybe this is x equals 7, maybe this is x equals 20. I'm plugging in different x values, and then I'm looking at the area under the curve from a to those different x values. Different x values give me different integrals, different values that I'm going to find. It is a function of x, all by a weird function. So the fundamental theorem is important for those two reasons. It shows this inverse-like relationship between derivatives and integrals, which is a very important idea, and it shows the existence of antiderivatives for continuous functions. When we're thinking about how to do problems with the second part of the fundamental theorem of calculus, there's really only one kind of problem we're going to deal with, and that is to find the derivative of some function like capital F of x here, which is the integral from 3 to x of t plus 2 dt. The second part of the fundamental theorem of calculus says that this is going to be equal to just x plus 2. It's like we're replacing the t with x. I'm trying to find the derivative of the integral of t plus 2 dt. And what the second part of the fundamental theorem says is that we can kind of just cancel out the derivative and the integral itself, and we're left with just the function itself with respect to x. That problem is as simple as that. There's really nothing else to do, but we're just going to show why this may make sense. We're going to think about just doing this problem a little more carefully. I want to find the derivative of the integral from 3 to x t plus 2 dt. So I'm going to deal with the derivative last. But to think about this integral, I need to find the antiderivative with respect to t. That's going to be 1/2 t squared plus 2t evaluated from 3 to x. I haven't taken the derivative yet, so I keep that notation. And when I plug in the top bound here, I'm going to get 1/2 x squared plus 2x. And then I'm going to subtract off, plugging in the bottom bound, 1/2 3 squared plus 2 times 3. And now I'm going to take the derivative of each of those things. Well, the derivative of 1/2 x squared is going to give me just an x. The derivative of 2x is 2. And the derivative of all of this, it's gross, but this is just a constant. And the derivative of a constant is 0. So this will give me x plus 2. Now we can go through that process if it's a nice function, but the next problem we're going to deal with is not that way. So we're going to do the same kind of thing. Find the derivative of the integral from -1 to x of x cubed plus 1 dx. In this case, we cannot find a nice way to write the antiderivative or an antiderivative of x cubed plus 1 in square root. It's not because we don't have the tools for it yet. There actually really is no way to easily write that down as a function. So we cannot go through the second way we did that last problem by finding the antiderivative and then taking the derivative. We just have to rely on the second part of the fundamental theorem of calculus. And we can do that. It's very, very quick. I should say that this problem should be a t in here instead of an x. To keep the variables separate. The reason we need another variable there is because if they were all x's, things would get confusing. But basically what we're going to do is we are just going to replace the t with an x, and then we are done. In the next section, we're going to learn about how to find antiderivatives in more generality, going backwards through more derivative rules, introducing the idea of substitution.